Good evening. My name is Denae Sheppard, and I'm going to be presenting Detecting and Identifying Faulty IoT Devices in Smart Home with Context Extraction. This research and paper was conducted by a group of researchers in the Department of Computer Science and Engineering at a college, University of Science and Technology in Korea. It was originally presented in 2018 at the 48th Annual IEEE IFIP International Conference on Dependable Systems and Networks. So during this presentation, we're going to introduce what is IoT. We're going to talk about what specifically they cover within the paper. We're going to talk about existing approaches to identifying faulty sensors in IoT environments. We're going to talk about solution requirements. We're going to discuss what is DICE, the experiment that they conducted using DICE, the evaluation of that experiment, and some other discussion points that they made at the end of their paper. Let's get to it. What is IoT? IoT is the Internet of Things. It is the interconnection via the Internet of computing devices embedded in everyday objects, enabling them to send and receive data. A smart home is a home equipped with lighting, heating, and electronic devices that can be controlled remotely by phone or computer, and this is a component of IoT. Smart homes and smart cities are becoming much more popular, so it's important that we focus on the upkeep and security of these networks. This paper will focus on IoT environments in the context of a smart home. IoT devices tend to be lightweight devices with limited computational ability. However, these devices can be exposed to harsh environments, which causes frequent device failures. There is not currently a good solution for detecting and identifying these faulty devices and sensors. During this presentation, we will discuss existing solutions and why they don't work, what DICE is and how it differs from existing solutions, and how DICE was evaluated. The main contributions of DICE are novel design. The faulty device detection and identification method enhances the reliability of smart homes. Usability. This method of context extraction does not require user intervention. Generality. This method works for both binary and numerical values. This makes it easily adaptable to real-world smart homes. Feasibility. This method requires a small computational time because this process has been simplified. And finally, promptness. This method takes an average of 3 minutes to detect sensor faults. For identification, it takes an average of 28 minutes, but in optimal conditions, this average can be reduced to just 7 minutes. Existing approaches. There are 3 types of existing approaches currently being studied. The first is a network level approach. There have been a few different solutions proposed to detect sensor failures on a network level. Some of these use a network management system that monitors packets to detect anomalies at the network level. One devises distributed sensor node failure detection method. One aggregates distributed data at the sink and detects failure by finding insufficient flow. And lastly, one uses the Markov model to characterize normal behavior. These solutions can effectively find sensor failure at a network level, but this is only when the sensor stops producing data. When failing sensors continue to report incorrect but technically reasonable values, the failures will be missed. This means they are not effective in detecting faulty sensors. Next is the homogeneous approach. This approach deploys multiple sensors of the same type to detect and identify a sensor that shows anomalous behavior. Most of the work in this approach exploits the fact that the same type of sensors that are spatially close generate the same values. In this approach, faulty sensors show uncorrelated behavior with other spatially close sensors. Another body of work analyzes time series data to identify faulty sensors. And finally, there's reputation-based framework, which uses correlations between neighboring sensors of the same type. Although many studies take this approach, the redundancy of multiple same-type sensors close together increases cost of deployment. Also, most of these systems use threshold-based sensors. Finding the optimum threshold for these sensors can be difficult, and the incorrect threshold data can decrease the accuracy of the system. This means that this homogeneous approach tends to have an increased cost, and it's not always accurate. Lastly, you have the heterogeneous approach. This combines different types of sensor data to detect sensor failure. There are multiple approaches to this. Here are a few. SMART, S-M-A-R-T, detects sensor failure based on classifier outputs. Failure Sense explores the relationship between electrical appliances and sensor data to detect sensor failure. IDEA, I-D-E-A, performs activity recognition based on sensor data and computes the sensor's impact for each activity. CLEAN, C-L-E-A-N, suggests a cluster-based outlier detection technique to detect anomalies in event-driven binary sensors. Finally, Sixth Sense devises a context-aware intrusion detection system for smart devices by monitoring changes in sensor data. The problem with current heterogeneous approaches is that they are not effective solutions. An effective solution for detection identification of faulty devices and sensors should meet the following 4 requirements. Usability, the condition in which a system does not require any user intervention in the form of required labeled training or supplying additional information. Generality, the system considers various sensor types and fault types that represent real-world settings. Feasibility, the condition of which a system does not require too expensive computation costs or does not make assumptions that are far from reality. And promptness, the condition of which system detects or identifies a faulty sensor properly. As we can see from the table shown here, most of these solutions only meet one of these requirements. DICE, however, meets all 4. Is DICE, detection and identification with context extraction. A typical smart home consists of diverse IoT devices, a home gateway, and a network that connects all of these devices to each other and to the internet. All IoT devices in the smart home are connected to the home gateway. This gateway is generally linked to some sort of cloud server. The DICE is installed on the home gateway. DICE consists of 2 distinct phases. The first is the pre-computation phase. During the pre-computation phase, the system extracts the correlation and sensor state transition information from the collection of IoT sensors and actuator data. Next, it moves into the real-time phase. During the real-time phase, the system performs correlation and transition checks to detect faults in real time. After detection, the system then analyzes the context to identify the faulty device. So first we'll look at the pre-computation phase. This is the phase where normal behaviors are collected. DICE records the context of the IoT environment by extracting the correlation among sensors and by computing the transition probability of the sensor state sets and actuators. Since actuators affect sensor readings, extraction of only sensor correlation is sufficient, and this reduces the complexity of precomputation. During this phase, we assume that all IoT devices are without faults. Figure 3 shows us the correlation extraction phase with the construction of sensor state sets and group generation. The sensor correlation is extracted from raw sensor data. DICE uses this raw data to construct a sensor state set. This sensor state set is composed of bits that represent the activation status of each sensor within a predefined time frame. DICE can use both binary sensors as well as numerical sensors, and it applies different techniques to set activation statuses on the two sensor classes. Ultimately, DICE will convert numerical sensor data into binary values. This minimizes the computational cost and achieves the generality and feasibility requirements. Because this correlation extraction method runs automatically and does not require any user intervention, it also achieves the usability requirements. Figure 4 shows the transition extraction. To extract the sensor state transition information, DICE computes 3 separate probabilities. Group to group is the transitional probability of the sequence of groups obtained in the correlation extraction. Group to actuator is the transitional probability from a group to an actuator. Actuator to group is the transitional probability from an actuator to a group. Now let's look at the real-time phase. In this phase, DICE looks for signs of deviation from the normal behavior collected in the precomputation phase to detect the presence of faults. Figure 5 shows us a correlation check. During this step, DICE converts the raw sensor data into a sensor state set as earlier described. Then it compares the obtained sensor state set with each of the groups obtained during the precomputation phase and makes candidate groups up to a certain distance between two different groups measured by bits. The distance threshold of the candidate groups is determined based on the fault models considered. When looking at candidate groups, a group that perfectly matches with incoming real-time sensor state set is referred to as a main group. The remaining are referred to as probable groups. If a main group is not present, this implies a new sensor correlation combination has occurred. When this happens, DICE regards it as a correlation violation and proceeds straight to the identification step. If a main group exists, then it proceeds to the transition check step. Figure 6 shows the transition check. In this step, DICE detects a transition violation based on group to group, group to actuator, and actuator to group transitional probabilities obtained during the transition extraction. The transition check is necessary because for sensors that are failing but still functioning, they often maintain correlation information even after the fault. DICE examines 3 cases during this process. If the transition belongs to one of the 3 cases, DICE regards it as a transition violation. When a violation is detected, DICE identifies the faulty device by diagnosing the problematic context in the identification stage. DICE compares the problematic real-time sensor state with the list of probable groups. It examines the bits that differ and finds the probable faulty sensor. If the difference bit is a binary sensor, we derive the corresponding binary sensor as the probable faulty sensor. For a numeric sensor, 3 bits constitute for a single numerical sensor. So if one of the 3 bits is different, we derive the corresponding sensor as a probable faulty one. If there is only one probable group, the user is notified of the probable faulty device. If there are 2 or more, then transitional probability is checked. If there are multiple faulty sensors, the identification step will continue to repeat until it has identified all of the faulty sensors. No matter if the identification stage is triggered during the correlation stage or the transition stage, the identification stage always starts with correlation checks. Now it's time to start looking at the experiment. First, we're going to talk about data acquisition. Table 2 shows the data sets that were used to show that this scheme is applicable to real-world smart home environments deployed with various sensor types. They used a total of 10 data sets. 5 of the data sets used were third-party data sets collected and distributed by Intelligent Systems Lab Amsterdam and Washington State University. These datasets have also been used in state-of-the-art sensor failure detection studies. The group also deployed their own smart home test bed so that they could get a well-rounded group of datasets with diverse sensors. So the last 5 datasets are from the smart home test bed that they created. Figure 8 shows us the floor plan for their smart home testbed. We can see the different sensors, actuators, and aggregators that they placed within their testbed. They placed a total of 37 sensors from 9 different sensor types. The sensor types used were light, temperature, humidity, motion, ultrasonic, flame, gas, weight, and location. They used a total of 8 actuators. The actuators they used were 3 smart bulbs, 1 smart speaker, 2 smart switches, and 2 smart blinds. And they used 8 Raspberry Pi boards as aggregators. All of this was connected via an Ubuntu server. The actions performed in the smart home test bed are the same as those in the third-party datasets. The other thing that they had to think about for this experiment was fault generation. Sensor faults fall into 2 separate classes. The first is fail-stop faults. Fail-stop faults occur when a device completely shuts down or its function ceases to generate data. These faults are unpredictable. Next, you have non-fail-stop faults. These faults occur when a device exhibits an abnormal behavior and generates incorrect data. However, non-fail-stop faults can be classified. The following 4 classifications are common types of these faults. Outlier. A sensor fault where the sensor value at some point, spatially or temporally, generates an anomalous value. Stuck at. When a series of output values is unaffected by the input and remains the same. High noise or variance. When a sensor values have a noise or variance beyond the expected degree. And finally, a spike. When multiple data points are greater than the expected value, making a shape like a spike. These 4 common types of faults were inserted into the collected data. Sensor type, fault type, and insertion time were chosen randomly. So let's see what they learned from their experiment. They had a total of 10 data sets that were evaluated. 5 were the third-party data sets and 5 were from their testbed. The first 300 hours of each dataset were used as the pre-computation phase. The rest of the available data was used as the real-time phase. The real-time phase data was divided into 100 segments of 6 hours each in length. Values to generate faults were inserted into each segment. If the data was less than 600 segments, then segments were reused. The original segments were used as faultless data, and duplicate segments were used as faulty data. In each of the 5 third-party data sets, 100 faultless data segments were tested and 100 faulty data segments were tested. So first we'll look at their accuracy. Figure 9a on the top shows the detection accuracy of each dataset. DICE was found to be highly accurate in detecting sensor faults in a smart home. Figure 9b on the bottom shows the identification accuracy of each dataset. DICE was also found to identify problematic sensors with high accuracy. The average detection and identification time of DICE was measured for each dataset. Detection time is the time DICE takes to detect the presence of faults since the occurrence of the faults. Identification time is the time it takes DICE to identify the faulty sensor since the occurrence of the fault. These times were proportional among the smart home test bed that was created, and with the exception of House A, they were also proportional among the third-party datasets. Table 3 In Table 3, they compared the detection time of the correlation check and the transition check for houses A, B, and C. This shows that fault detection by transition check is approximately 3 times slower than the fault detection by correlation check. So, for computational time, computation time of the correlation check, transition check, and identification from the 10 datasets were measured to verify the feasibility. As you can see, the shortest correlation times were between houses A, B, and C. The maximum computation time per one sensor state set in real time was well below 50 milliseconds for all datasets. The time of the transition checks and identification was negligible and similar across all datasets. All of these times were reasonable, which means that computational time meets the feasibility requirements. Correlation degree is an indicator of how much correlation there is among sensors. The more sensors there are that react together, the higher the correlation degree. So to quantify the degree of correlation, they calculate the average number of sensors per group. Table 5 shows the summary of this correlation degree of each dataset. This shows that the number of sensors and correlation degree are not directly proportional. Datasets with higher correlation degree achieved better detection and identification accuracy. Lastly, we'll look at the ratio of detected faults. They analyzed the ratio of faults detected in the correlation check and the transition check. All fail-stop faults were detected during the correlation check. Most stuck-at faults were detected during the transition check. The researchers felt that the transition check is essential for checking non-fail stop faults. So with all of this wonderful data they received on DICE, there were still a few things that they wanted to touch on. First is multi-user cases. DICE can be deployed into a smart home environment with more than 2 residents as long as they are present during the pre-computation phase. This does, however, grow the number of unique sensor state sets exponentially. To resolve the problem, users may group sensors that are spatially closely located and connect such a group to DICE individually to restrain the growing number of combinations. For example, DICE may be deployed in the kitchen independently from the living rooms or bedrooms. Next, they discuss multiple fault cases. Multiple faults may occur simultaneously in a smart home. 3 faulty sensors were randomly selected to generate faults simultaneously so that the results could be examined. The average precision and recall for identifying multiple faulty sensors was 79.3 and 63.3 respectively, which is considered to be within the reasonable range. Next, they discuss the impact of different parameters. The pre-computation period affects the accuracy of DICE. If this period is too short, DICE may not extract enough context to represent normal behavior. The longer this period, the higher the precision. The segment size and duration of the sensor state set also had an effect on the accuracy of DICE. Lastly, they started looking at security. DICE can detect malicious numeric sensors in addition to binary sensors. However, it cannot detect passive malicious sensors or information leaking sensors at this time. The team, however, is currently working on enabling DICE to complete these tasks as well. I thank you very much for listening to this presentation. I found this paper particularly interesting. Unfortunately, I did not have a time to really get into a lot of the nitty-gritty of the research, so please take the time to read the paper. It's a great read. I hope that you all enjoyed it, and thank you for watching.